Hi everyone. I want to talk a little bit about common tangents. So here we have two circles and a line that is tangent to both of them. So we call this line a common tangent to the two circles. And in particular, this is a common external tangent, as in some sense it's on the outside of both circles. We'll see more about that in a second. Common tangents have lots of interesting properties, and we can see some of them by doing what we often do when we have a diagram involving two circles, and that is we construct the line through the two centers of the two circles. So notice that when we do this, we get this point of intersection, and this diagram is a similar triangle diagram. We have this triangle CYP similar to CXA by angle-angle. They share this angle and these two right angles. So notice that this right triangle is similar to this right triangle. So anytime you have a common tangent, you have this similar triangle diagram. Now, in the common internal tangent situation, which is like this, you also get those similar triangles when you construct the line through the center. It's slightly different, but the same basic idea persists. So these two triangles are similar by angle-angle. Here you have the vertical angles that are congruent and then the right angles. And so these two right triangles are congruent, or are similar, rather. And so regardless of the nature of the circles, or whether the tangents are internal or external, then you have this similar triangle diagram that always exists. Moreover, something really interesting you can do with this line through the centers is you can see that this line is actually a line of symmetry for the diagram, which means that if we reflect these objects over this line, then we see that we get the tangent on the other side. So we can construct this line, and sure enough, it passes right through C. So these are the two common external tangents, and the line through the centers of the circles is the line of symmetry of this diagram. So these triangles are congruent, and all that similarity is preserved, and of course it doesn't matter how we move things around. The same thing is true in the internal tangents situation. We can reflect all of these objects over the line. And then we can construct this line through them. And not only is this a common internal tangent, but this whole diagram is symmetric. This is a right angle. These triangles are congruent, and so on. So there's a lot of power in these common tangents, whether they're internal or external. As a little challenge, I'll just suggest to you that there's something really neat that happens when you have two circles that are themselves tangent. So these circles are called mutually tangent. And in this situation, the length of the common external tangent segment, this, is kind of special. Oops. So this length xy in this diagram is related to the radii of the two circles. So you have one radius and the other radius here. This distance between the two centers is actually the sum of the two radii. And with a clever addition to the diagram, you can figure out the length of xy, and it turns out to be something familiar from a few weeks ago. So I encourage you to play around with that and give it a try.